All right, welcome to the last video of the Monte Carlo lecture. And here we're going to talk about one specific method of reducing the variation in estimation due to simulation. Now, up to this point, we've been randomly drawing from distributions. This allows us to have the statistical and probabilistic arguments associated with the unbiased nature of the estimators for the integrals that we're working with. We're going to trade off a little bit of the benefit of the statistical arguments for the practicality of reducing variation. As I mentioned at the end of the last video, when you draw a random sample, they vary somewhat, so the calculated values of your interval will vary somewhat. So think of it this way. When you draw a random sample from a normal, let's say, just picking a distribution, you might get a couple here and a few there and one and a few and one and a few more here. But they will be chunky and not a smooth distribution. So the sample will be a histogram that will vary each time you do it. And this is all well and good, but we can address that a little bit by being a little bit more systematic. The main thing is we want kind of a histogram in here that we can use to calculate our integrals on. So maybe what we do is we systematically chop this space up into kind of equally spaced points, and then we collect our data by the distribution accordingly. And the way to think about that is actually in the sense of a CDF, and this is my x, and here we got 0 to 1. What I want is, instead of a random sample of uniform variables, which could be very chunky, I want a nice systematic, almost grid, you could think of it, of points. And then as all those points come across, these points here will be much more concentrated because at the steeper slope, these points out here will be spread out, and eventually what I end up with is a histogram that is much more, not very symmetric, it should be symmetric, but still much more kind of filled out. Now, just using a grid of points can do this. It does completely drop out all of the mathematical proofs behind the consistency and such of these integrals. And we can recover the value of that by adding a random component to this, and we take our proofs in accordance with these particular random components, and I'll explain how that's done in just a moment. And so instead of using just a grid of points, we are going to use what's called a modified Latin hypercube. There are other ways. Before this was used, I used what was called a Halton sequence, and it had its way of doing things. But this is so much easier, and the practical results don't vary, that I've dropped using the Halton sequence, and I just specifically go to the modified Latin hypercube. It's so easy to program. But there are other methods that one could use to do this, and the Halton sequence being one, the Latin hypercube here being another, and then there are many, many other ones as well. In class, we're going to be using the modified Latin hypercube, or you can just do a random draw and compare the two and see. So here's what we do. We decide that we want to draw n number of values. Before I was calling this R, but n number of values, which basically means if I were to do a grid, I want n grid points is the idea. So I am going to create a function here, phi of j, where j is my index from 1 to n, and it's j minus 1 over n. And really what that's doing is that's identifying points starting at 0, and it'll give you n points evenly spaced up to 1/n of the interval short of 1. Okay? So it'll start with 0, because when j is equal to 1, phi is 0. And then when j is equal to n, it's n minus 1 over n. So 1/n of it is this side. So here would be your phi at n. And over at this end is your phi at 0. Okay, so we've chopped up this interval, even number of spaces, and we end up the last point of phi being just 1/n shy of 1. Now the key to this is we're not going to use these specific points. We are using these as kind of bins, intervals, within which we're going to pick points. So how we do this is we're going to draw a uniform variable, 0 to 1, and here again are our bins, all the way up to the phi n here. And we are going to draw a uniform variable, multiply it by 1 over n, or take it divided by n, and call that, for the moment, x, the scalar. That's going to span the distance from 0 to 1 over n, right? Since u goes from 0 to 1, x will go from 0 to 1 over n. In other words, it spans a distance of the width of our bin. So now what we do is we take and create this kind of capital phi of our original phi, which is the lower bound, right? So here is phi 0, let's say. So we start here, and we're going to add a random component distance that could only at most go just up to phi 1. So it's going to pick a point in here. Now the next one at phi 2 is going to be little phi 2 plus x. It's the same x, so we're going to use the same distance across the board. Then it's going to be somewhere between the phi 1, let's pick this at, actually we'll just pick this now at phi 1. So it starts at phi 1 and it adds x to it, and it will pick this point here perhaps, and it'll go the same way all the way through. Now the advantage is all you've really done is you've just taken as if you started with this grid, and for each person you just shift all of the points in equal distance this way. Just take the whole thing and shift it. And this is the case because you will draw a random uniform variable for each integral. So anytime you want to calculate an integral, you will draw a uniform variable. Now, in what we do, we're going to need an integral for every person in the data set. So if there's 100 people in the data set, we may need to calculate 100 integrals. So what we'll do is we'll assign a randomly generated u, a single value, for each person. So each person will have a different value, but that's that one value that will shift all of their points over. So that means each observation has a different shift. That's the randomness that the mathematical proofs can take advantage of, and we're not going to concern ourselves with the mathematical side of that. But so if you then look at the capital phi and you take a difference, you'll notice they all, in fact, have the same distance of 1 over n between them. And so they're all equally spaced, but each integral is calculated by a random perturbation, essentially, of that. So again, what we have here is I've chopped this up in terms of n points, in this case 6 I'm showing here, and actually I can do that, and perhaps my x, which is equal to u over n, is equal to 0.5 over n, or half the distance, then this person will pick these points here. Perhaps somebody else will have instead 0.25 over n for x, and they will be only 25% of the way, a quarter of the way in each of the intervals. So the blue hash marks are the sequence for somebody who ended up the random draw of 0.5. The green ones will be the sequence used for somebody whose random draw was 0.25. Each person in the data set may get their own random draw, so they will be randomly perturbed in terms of the sequence, but each one will have the same distances between them. The green from the green will be the same as this blue from the blue. They're equal distance, and all the distance will be the same as the bin, which is the 1 over n size. So this is one way of reducing the variation due to simulation. It's called modified Latin hypercube, and this is the primary method that you will be using in class as an alternative to simply doing a random draw. And as I say, that I use this extensively. Sometimes I use random draws, but for the most part, I will use modified Latin hypercube. In this day and age, you can get away with a fairly large number of draws, and consequently, computationally, and consequently, the ramifications of using the modified Latin hypercube can be somewhat mitigated, because you might find it just as simple to just draw a large number of a random sample. But nonetheless, the modified Latin hypercube can allow you to draw fewer values and get the same variance in your estimates. So this ends the sequence of lectures on Monte Carlo, and we will then move into lectures on maximum likelihood estimation, starting in the next sequence.